Hi, we're Team 27, and for this project, we're working on the topic brain tumor detection using convolutional neural networks. My name is Harsha, and working with me on this topic are Arun and Britannia. Our motivation for picking this topic is because brain tumor is one of the most hostile diseases in the world, with over 700,000 cases in the United States alone. The diagnosis has to be accurate to prevent any fatal error in treatments and increase the life expectancy of the patient. Generally, the MRI scans are evaluated by human doctors like radiologists or neurosurgeons for detection, but this could lead to a few problems like the presence of a shadow, which makes the tumor identification complex, or the time it takes to identify the tumor correctly. So, to reduce these fatal human errors, machine learning can be used for automatic classification. For this project, we have a baseline model that uses CNN with a validation accuracy of 84%. In our implementation, we plan to use a better optimal CNN model with the ability to detect the kind of tumor in the image, and we plan to further implement faster RCNN on top of it to identify the location of the tumor using image segmentation. We got a dataset from Kaggle, and this dataset contains 3,565 raw images with tumors in different locations of the brain. The dataset is broadly classified into four categories: glioma, meningioma, pituitary, and no tumor. Each image is of varying sizes, and we reshaped it into three channels with dimension 300 cross 300. Now we look at some of the sample images randomly chosen from the dataset. As you can see, the images are labeled as the four categories mentioned before.
We chose to use a paper for our baseline model. This paper experiments with 5 different variations of CNN architectures to conclusively find a high-performing model for brain tumor classification. Throughout the paper, they experiment with hyperparameter manipulation to affect the validation and training accuracy and loss. After all their models, we decided to choose the one that was more consistent, and it decided to use the Atom Optimizer. The model we chose to use as our base model was their best performing CNN architecture. The CNN architecture is as followed. This model is split into many layers. Their first layer is a convolution layer with ReLU activation, followed by a max pooling layer. This order is repeated 2 times before then being flattened. This is followed by 2 fully connected layers. The implementation of the architecture produces 4 parameters that determine the success of the model. The success is defined as a model able to accurately classify the input image by matching its label to the image. The 4 parameters are the loss and accuracy of the training and validation set. Accuracy is the percent of the current guesses. Loss is the error for inaccurate predictions. The model resulted in an 84.2% validation accuracy and a 98.51% training accuracy. The validation and training loss showed a decreasing trend with respect to the number of epochs as they increased. The model had medium performance due to the validation loss not showing a perfect decreasing pattern. Similar to the baseline model, we chose to use the Atom Optimizer in the learning process because of its ability to handle parse gradients on noisy problems. We chose to include 4 convolution layers. In addition, we added a dropout layer with a rate of 0.5 sandwiched between 2 dense layers. The CNN architecture flowchart can be seen on the right.
From the plot, what we can see is that the training loss and the validation loss is decreasing continuously as the epochs are increasing. Final loss for validation is around 0.38, and for training, it is 0.13. From the accuracy curve, we can see that the training accuracy and validation accuracy is increasing as every epoch for training. So this model is good fit for the current data. And the overall validation accuracy is 91.68, and for training it is 94.39. Here we have the confusion matrix and the classification report. The classification accuracy for glioma is 100%, and for meningioma it is 85%, and for no tumor it is 84%, and for pituitary it is 97%. And here we have the comparison between 2 models. So one of the key difference between these 2 models are like the number of classes and the image resolution. In the baseline model, there is no classes for no tumor, and in the proposed model, we have that. And we also have a difference in the model structure. We have two additional convolution layers with different filter size than the baseline model. We also have a dropout layer. We added this because to reduce the overfitting. And after training the model, we saw some more changes in the loss and the accuracies. Baseline model is better for training, and proposed model is better for validation set. And yeah, comparing these two, we can say that like proposed CNN model is better than the baseline CNN model. We have also proposed to implement image segmentation using faster CNN, but due to the dataset constraints that we do not have the bounding boxes or labeled image annotations, due to which we are not able to implement fast RCNN and image segmentation. Yes, thank you.